Right, so welcome to this lecture. I don't remember the lecture number. Is it 12, 13 something? So after the mid, um, we have been discussing important modules in random processes, right? And where did we start? We started with the idea of uncertainty, right? So we brought uncertainty into our parameters, into our equations, and all those things, yeah? So once we had done that, we said, okay, let's make the uncertainty more formal. So we went into the Kolmogorov axioms, defined all the sigma fields and all those things. So we defined some sort of probability measure, yeah. And then we said, okay, now once we have studied different probability measures, some basic formulations of probability, we decided to go for how to collect these measures, yeah. So we went into what different kind of probability functions, right? So I will call them probability functions, yeah. That means density function, cumulative but in the end all of them one way or the other were collecting these measures in some way, yeah. After that, where did we go? Our third model. So there one of the most important guy was this thing, probability density function and the cumulative distribution function, right? So once we have done that, where did we go? Moments. Why did we go to moments? So
It's a representative of moment.
yeah, so because these are too much information often, too hard to tackle, yeah. So we went to the proxy of these things, which are some features we extract from either directly from the data or from their distribution, and that was the module on moments, right? So once we had done the moments, so what were the key moments we saw? We saw the expectation operator, right, and the variance and covariance for two random variables, right? So we saw all those things. Let's see, for these guys I will change here. It's still taking time, so we will see. So after moments, where did we go? So until here, mostly we were dealing with random variable.
Right.
Yeah? Even when we are dealing with two, just handling them, just two, not more than that. Yeah.
The joint
Then we
distribution.
went on to
Joint distribution,
yeah,
then random process.
random process. So from there on, we went into the random process, but we didn't really define a particular random process, right? All we defined was some classes of random processes. So how did we classify random processes? By what categories or what methods did we classify them? Do you remember?
By varying t and x, whether it can be discrete or continuous.
Right. So we classified them by their state, which was the x-axis. We classified them by their time, the values they take. Was it continuous or okay? What else classification did we do? Badi ahem wali, very important one. Last thing we did.
Stationary and
Yes, yeah. So we classified them by their state, by their time continuity or not, and then we classified them by their stationarity. Yeah. So we said there is a huge subclass within random processes, which is the stationary random processes. Yeah. And we did the concept of that, and then we defined precisely what it meant to have a random process, right? So I think this should be good enough for these guys. We will keep this here. Right, so with stationarity we stopped at defining stationarity formally. So can you recall with me what was it? Stationarity.
If I have a mean or constant, there are the two conditions that will depend. Mean and variance must be constant.
And time difference between 2 points is same.
That is a White-Hand stationary.
Time difference is
Same between two.
no
different.
time difference same
Depending
with
on
what?
time difference.
The
So we have mean is constant and mean is dependent on time difference.
variance or
Yeah,
covariance?
Covariance difference.
Covariance, right? So the covariance which we had defined as what? So covariance between xs and xt, which we had defined as rs or denoted as rst, which said it should depend only on the difference s minus t. Yeah. So the absolute of actually s minus t. Yeah. So because of the nature of covariance, we know it's going to be symmetric if it depends only. It has to be symmetric, but it has to depend only on the difference of s minus t. So in a way we are saying it should depend on this difference. Yeah. So then we said, okay, then we don't need to, once we realize or are able to prove that a function is like that, then we can say this is xt plus tau and this is xt and then r t plus tau and t, but the actual t doesn't matter. So we said we will rewrite this kind of functions based only on their time difference, right? And that was the lag r tau. Yeah. So basically this is where we stopped last time. There are a few more discussion points in here, especially the properties of r tau. It has to be symmetric, it cannot be negative, okay, and then its value at r0 should always be greater or equal to its value at any other tau. So there are like many properties that we require or that are proved for the covariance function of a wide-sense stationary process. So it's there in my notes. I leave it to you to read through. That is the last 2 pages of lecture 5 in the slides, in the notes. Okay, you have those. Go through them. They're also in your book, Lindgren. Go through those. They're proofs. They're not too hard. But the benefit of knowing those properties is what? We can analytically work with that. Okay. Right. So we will do that. Firstly, let's do this. आपको दोनों एक में चाहिए सेपरेट चाहिए एक में चाहिए शॉर्ट
मल्टीपल सोर्सेज ऑफ यूज करके मैं कुछ एक्सप्लेन कर रहे हैं
राइट okay so right, we have this here. Yeah, so basically we have seen this before, that random processes show up in different fields. Yeah, we saw that it shows up in communications, it shows up in biomedicine, in finance. From finance, can you think of an example of something which is a random process? Stock market, highly non-random, highly random process, right? If people could predict this very well, they could become billionaires overnight. But this is a highly random process. In fact, we will see that it's also highly non-stationary and it's non-ergodic. We will see those properties later. Yeah. So, but here we had previously shown you what are the, let's say, applications of bringing in randomness into our mathematics, right? Most of the applied mathematics that requires you to work with real data from communication, from finance, from instruments that measure different vital signs, chemical processes they measure. Most of it has randomness in it. Okay, and the more we are able to work with that randomness, the better we are equipped to handle changes in that data, right? So we have discussed that before. So again, back to our part here. Can any of you think why this might be? So just go through those properties. As I said, it's good to know them, and they are analytically helpful when you are solving some analytical expressions. You will be using these properties. I think we mentioned 6 or 7 of them, but can you talk about this one quickly? Why should this be?
It's actually the covariance, and it's saying that the difference will be very small between them.
Hmm.
So the covariance will be high when the difference is large, then the covariance.
There is no requirement like that. There can be a random process where the 2 points that are very close to each other, yeah, are not correlated or very low correlation, but 2 points very far from each other are highly correlated. There can be, and there are processes like that. So then why do you think this property should hold for a wide sense stationary random process? Think about it. So, what is R0? Let's start with that.
When t is equals to s.
Yes. Yeah. So, what is that?
When we have same random processes. Time difference when 0, when we x ss, yeah, x tg, that's kind of random.
So, you are R0 is covariance of xt with xt, right?
That
That
x becomes variance.
that is fine, but that is the covariance of a random variable with itself. A random variable with itself should be most highly correlated, right?
Yes.
Cannot be same, Anna. They are exactly the same. But this thing says, okay, it could be the same, close to that. Another random variable, which is not xt, may have a correlation as high as the original, but it cannot go above that, because that is the most you can get. The way as you said, this becomes the variance. But if you find the correlation, you normalize it, you will find it's 1, right? You cannot go above 1 in correlation, right? So basically we are saying this is the covariance of the random variable with itself. What was covariance? Degree of linear dependence. Can there be more linear dependence than a random variable itself? Imagine drawing xt here and xt here, s equals t. What should you get? Always a line, right? So it should be 1. The correlation should be exactly 1, full, maximum. Yeah. So that's what we are saying here. Yeah. So similarly there are other properties. I want you to go through those. I will quickly check if we are still recording. Yes. And we had Shazad going up there. Hopefully that part is not, yeah, it's not true. Okay, so today's lecture is now next thing. Okay, this is more of a wrap up of what we had here. Please read through that on your own also. Today's lecture is over here. What is that? Yeah. Here we did not talk about actual random processes. Yeah. Now today we are going to talk about some common random processes. So far we have been talking in abstracts, classification, this, that. Yeah. Today we actually now go into, okay, this is one random process, this is another. You know some of them, right? Brownian motion, random walk, those things. So this whole module, which is rather big, I think, is about, if I don't forget, it's around 10 different random processes, starting from a single random sinusoid to a moving average random process to let's see, the discrete time Markov chain to random walk to Brownian motion. All of these are now instances of random processes, and we will apply a lot of what we already learned. All of this was needed to properly define, analyze, and discuss these processes. Um, Point and counting processes, renewal processes, birth death processes. कौन कौन से सुने हुए हैं? Birth death वाला.
First we bird depth in the process.
Right. Renewal processes. You have heard of its special case, Poisson, most likely. But not today. Towards the end of this module, we will see how birth, death, renewal, Poisson, how are they related.
Sir, that's kind of random walk, Levy walk, and polygon billiards. ये process है.
सुने हुए आपने? Right.
पढ़े भी सर ये.
किस कोर्स में?
Polygon billiards process जो वो भी random वो. So it आपको पता है.
Right. चले अच्छा. So Levy will come in another lecture. We will also see that when we go into details of Poisson and Gaussian, then we will come across Levy processes. But for the first exposure, I have looked into more broad or more common types that show up, right? So let's start with the first one. Very simple, a sinusoid with random amplitude. Okay, and there is something very interesting in this process that we could look at. So a process could have very smooth realization, as smooth as a sinusoid, but still be random. Okay. So now if you draw a sinusoid, it doesn't look very random, yeah, but you could make this whole thing random by an interesting trick. Let's say, so this is our first process. I won't write that, I need space. So first a sinusoid with random amplitude. Let's say I'm going to take the values xt from a sinusoid sine t. All good, nothing special so far. If I put an amplitude here, still no big deal. You know it from basic mathematics. It's a sine function with adjustable. You fix 1, 2, whatever value you want to put here, you get sinusoid, right?
Yes.
With increase or whatever you set here. Now we bring in our friend uncertainty. Okay, so this is more of a toy example basically, okay, to get things started. But we bring our friend uncertainty. We say y is a random variable. Okay, and I say that I'm going to pick the value of y as 1 or 2. Okay, so how I'm gonna pick it? I could define a random underlying process. Let's say I will toss a coin. If it's a head, y is 1. If it's a tail, y is 2. Right? Now, depending on before the coin is tossed, yeah, can you tell what will be the value of this sinusoid at ta or any other point t equals ta?
We cannot tell exactly, but we can calculate its expectation.
Yeah, we will come to that later. But you cannot tell that, yeah?
Exactly.
But you know it will be one of two values, don't you?
Yes.
So this sinusoid is either has an amplitude of 2, right? So like that. Just imagine it's a nicely drawn sinusoid, okay? Or it has an amplitude of 1, in which case it goes, sorry, so its amplitude will have to be less, like that, yeah? Now, I already know that at t8 has to be one of these values, but what I don't know is which one, right? So we have brought randomness into this thing, and before you have tossed the coin, you cannot tell which value it will have. Yeah. What you can tell is the, let's say, the mean value or the range or the possible values. Like in rolling a die, you already know you cannot see a 7. Yeah. So here also you know you can either see this or this, but between them you don't know until this die is cast, right? So what do we call, basically this is one realization of the random process.
Yes.
Remember, before you have seen realizations before. When you roll a die, yes, outcomes were 6. When you see roll the die, you see 4. That is one realization. What's the difference here? Notice there the realization was not indexed with time, right? The realization was just static, one value, 4. Here the whole realization is indexed by time, right, and by a sinusoidal wave, but one outcome leads to this whole new indexed process that will be this thing. So this is one realization, this is another realization. Together realizations are called, I don't know if I have mentioned this before, but I can mention it now. All the possible realizations of a random process together are called ensemble. This word will come in handy in the next module when we go to ergodicity. We will come back to why we need this word. Ensemble means collection of all possible outcomes of a random process or a variable. So for the rolling a die, the ensemble is 1, 2, 3, 4, 5, 6. For this example, the ensemble are the two sinusoids. Yeah. So one realization, it has only two possible. The way we set it up, it has only two possible realizations. Now, bringing in what we have learned about these, why did we do all those modules before coming here? Yeah. So to analyze these things, we are dealing with randomness. So we will need this, we will need this, we will need this, depending on the situation. So let's start with this first, this classification. Firstly, is it a stationary process or not? What do you think? Or let's start with White's stationary, the easy case. What's the test for White's stationarity?
Mean is constant and covariance depend
On the S minus T.
minus
Yeah.
T.
Yes, sir.
So then, what do you think?
So
You wanna try it out?
Variance of
What will you always start with the mean? Okay, just a hint. Always start with the mean. It can save you a lot of trouble. If it fails, you don't need to go to covariance, right? So don't start with the hard test. Easy one is it. So
It's a mean is a function of time or a constant.
mean is a function of time. What's the mean?
Mean is 3 by 2 sin t.
Is
3 by 2 sin t.
okay. So you also found the mean value here.
Yes, sir. Mean of
Okay.
y find किया है sir.
Yeah. So even if you don't calculate, yeah, you calculate based on this. Yeah, but for the general case also, we can see that it's going to be EY,
Sin
which
t.
is a variable. So it's just whatever it is. Yeah. But we can see that E of xt is actually E of y sine t. And here you have already used properties of the expectation operator, haven't you? You see, when you take E of xt, you actually take E of y sine t. but then you had learned that this is not random, so expectation operator doesn't really apply to something that's not random, so this comes out as it is, and then you're left with EY, which I will just write here. So in a way you did that, yeah. And then the mean, now look at the mean. Expected value of x1 at some point t at t is dependent on the sine t time. So it's a, you don't even need to go to the second test. It fails the first test.
Yes.
So we will mention that, or it is मतलब ये मैं assume क्या होगा कि expectation का हमारे पास random variables का ही हमारे पास operator होगा. The expectation of the deterministic उसमें उपयोग होती है operator. So
yeah, what we're saying is that the expectation of this guy is basically sine t itself, right?
You're considering it's a number actually.
The
Yeah.
constant. Yes.
Yeah. So a constant occurs 100% of the time. Yeah. So you could look at it that way also, and it cannot be dependent. So you can separate also the expectation operators. Yeah. So then you are left with this thing. So since it fails the first test, we know it's not wide sense stationary. So even a process as simple as this may not be wide sense stationary. Yeah. Okay. So now we are ready to go into more realistic models, which is one of the most important ways of modeling random processes. You have learned ways of modeling deterministic related variables, right? Processes like functions. You have the linear function, the quadratic function. What else? Logarithmic function, sinusoidal function, right? So like those are important in general mathematics, basic mathematics. This moving average and the others we see today, they are very important in modeling random processes. Okay, so this one is what we call a moving average process, MA we write it. So this is the second. First one was what? Sinusoid with random amplitude, right? Second one for us now is the moving average process, MA. Okay, and its kind of friend, the autoregressive process, which will come maybe not now but after some lectures, and together they form what is called ARMA, autoregressive moving average. And this is one of the, together they form like one of the key modeling methods for random processes, okay, for random data. So but we have to build slowly, so we don't want to go to ARMA directly. We will start with moving average. So let's say you have a sequence of independent random variables, each with fixed mean. I'm going to just set it to 0 and variance sigma square. Okay, so the foundation is that you have a sequence of random variables ut. They are independent of each other. What does that mean? Yeah, so that means probability ut given us equals probability ut, okay, as long as t is not equal to s. Okay, if t is s, then you're saying probability ut given ut which should be 1. Yeah, that. So as long as t is not equal to s, the knowledge of the other one does not help. That's the basic formula, right? But it had what implications did it have? Remember, the distributions were separable. The expectation operator was separable. Remember?
Yes.
What else? The covariance was 0. Right? Separable. Yeah. So it had implications. This assumption, we are not asking you to prove it, we are starting with this assumption. assume that you have a sequence of random variables which are independent of each other. Each has mean 0, so EUT equals 0 for all t, okay, and each has fixed variance, that is V of UT is some, let's say fixed one, yes, sigma square. Notice no t here. Okay, so this is the assumption we start with to establish our or form our moving average process. So let's say I define a new process now. This happens a lot in random variables and random processes, that you start with some set of random variables, simple ones, and then you define a more complicated one based on them. Okay, so this is more like the raw material. It often shows up independent, fixed mean, fixed variance. It shows up in a lot of formulations. This is more like the raw material. Alone it has not much information for us. Why? Because it's independent, so mean is and all you can talk about is mean and variance, which are here. So let's see. Let me define a new random process which I will call xt, and this I'm going to call it as ut plus 0.5 ut minus 1. Okay, so now this random process is what I am interested in. This is a new random process. How is it made? This will also explain the meaning of moving and average. Yeah, at any given point, let's say I have here, since I've written this, so I will start here. Let's say I have U10, U11, U12, U13, U14, so on and so on. Yeah, without bothering about initial conditions at the moment. Let's start here. So what is X10?
U of 10 plus 0.5 U of 9.
Right. So it is these two, and it is kind of an average in the sense it's a improper average. You know, proper average would be dividing both of them by 2. Yeah. Here we are giving them. Sometimes we call it weighted average. Right. So this is a form of an average. So you are adding the two and dividing one of them by 1 and the other by 2. Yes, always. That is where the word average comes from. Okay, but where does the moving come from? Any idea?
T is varying, so there might be another
so
pair.
Imagine what would X11 be?
That going to be X11, X10.
U11.
U11
U11, U10.
So notice the window is sliding.
12.
U11, 10. उससे पहले वाला 9, 10 होगा दूसरे वाला.
Oh, अच्छा, sorry. Yeah, you're right. So we could make our life easier by just making it t plus 1 for now. Okay, in this case, it doesn't matter. Yeah.
Yes.
It could be like this also, but okay, we can do this. So I can make it easier. Let's do it like this.
They will be consecutive in either case.
Yeah.
We just want to say that.
Yeah. So X11 in that case is this thing, and X12 is this thing. What is X13? The average, the non-proper or weighted average of 12 and 13. So notice, it seems like there is this window that is moving, isn't it? नजर आ रही है window जो है ना, it's slowly moving. So when you are at X11, the window is on these two, focusing on these two. When you want to go to X12, the window moves to become this one. Then it moves to body मैंने बनाई है, so you can see, otherwise it's hard to see. And then it is moving. So that's where the word moving comes from. You are taking average of 2, then moving next step, taking average of 2, moving one step, moving, and each time you do that, you are getting x1, x2, x3, x4, x5, and so on. Right?
It will be discrete in that case.
Yeah. This is discrete. Yeah. Okay, so now what we want to do? We want to ask a couple of questions about this moving average process. By the way it is formed, we can call it moving average, that's fine. Now, depending on or based on what we have already defined, what do you think? Is this process wide sense station? XT. We have already talked about the raw material, yeah? But now this new process that we just formed and we named it moving average because that's what it's doing. Now let's look at its properties. Is it wide sense stationary?
First property holds. For mean is constant and variance function.
Also, just think about this thing. We know UTs are independent, right? But are XTs independent? X2, X3, X4, X1 and X2. Do you think they will be independent? Or let's say, make it easier, uncorrelated? What about X? Let's start here. X11 and X12, do you expect them to be correlated?
They are not independent.
They are. Do you expect them to be correlated?
Yes.
Okay. What about X11 and X13?
They are uncorrelated.
Why are you saying that?
Because there is no joint pair.
Yes, you can already see 11 and 12 have this shared thing. What is the shared thing?
U11.
U11. 11 and 13 don't have anything shared. Yes, so we expect that the consecutive two, the two adjacent to each other, in every case, we expect them to be correlated, but the one farther away. So if now I form a sequence of x's like x2, x3, x4, x5, what I expect is these two to have some correlation, these two to have some correlation. But if you make the jump bigger between here or even bigger here, no, zero correlation, right? We can show that also. So firstly, as you said, it passes the test of the mean. Yes, the mean is constant. You need me to prove it or you get it? So E of xt is E of ut plus, yes, 0.5 E of ut minus 1, 0, 0. And it didn't even bother about t, it's just 0. It doesn't have to be 0, it could have been any other constant, right? And it would have stuck to the same value. Now let's see, does the covariance RST depend only on the difference? So can you try to prove that? You have already answered intuitively, yes? But now try to do it mathematically. So start with covariance of XS, XT. What is it going to be? पहला स्टेप क्या होगा?
Covariance of x u of s plus 0.5.
Yeah. So for substitution, yeah.
Yes,
Covariance of u of s
plus 0.
plus 0.5 u of s minus 1 with
U of t
t
plus 0.5 u of t minus 1.
1. Now we know something about covariance
Yeah,
function.
The property we'll use.
Pairwise.
Yeah,
Yeah.
us ut minus 1.
us with
ut minus 1.
UT.
so we do pairwise, yeah.
Yes, the pairwise.
And then plus
US 0.5 UT minus 1.
so covariance of us with 0.5 ut minus 1 plus covariance of 0.5 us minus 1 with ut plus covariance of 0.5 us minus 1 with 0.5 ut minus 1.
Yes.
Now this seems a bit intractable in general, yeah. So what do we do? We need to reach a conclusion. Does this depend on S or S and T, or does it depend only on their difference? We need to reach that conclusion. Yeah, you have already answered that. You know, from here, what
sir.
was it? It only depended on the difference. As long as the difference between these indices was 1, there was correlation. Why is that correlation fixed? We will see that. But if you go above, it disappears. Okay, so how can we attack it? One way is to
This one, if P equal to S,
yeah.
these are the
Yeah, so try a few values. That's the thing. Yeah, so let's start with, as you say, S equal to T.
Yes, no?
Okay, so if you set X equal to T, what do you get?
Coherent.
So we set S equals T, what do we get? Try it, give me the answer.
Variance of
This is R S T, yeah. Isme, you just input it here, yeah.
Yes, sir.
So
SS variance of US आ जाएगा सिंपल.
The main वाली सर ये 0 हो जाएगी इंडिपेंडेंट है.
यूज हमारे पास इंडिपेंडेंट है ना सर, तो हमारे पास ये जो वैल्यूज आएंगी ये हमारे पास जीरो हो जाएंगी.
this one,
Yes,
zero.
zero.
हो जाएगी.
Agreed? Fine, good. What about this one?
ये variance of S.
variance of US.
Variance of
Variance of S.
U. US ये U की जो मर्जी कह लें.
What is that?
yes.
Sigma is
Plus. What about this one?
Variance of
0.5
बाहर आ जाएगा.
sigma.
Is that correct, or are we missing something?
0.5 दो दफा बाहर आएगा. 0.5 0.5 0.5
For variance, by definition, if there is a number here, it becomes squared, yeah?
Yes, sir.
So 0.5 ka square?
0.2.
0.25. You can try the definition. We have written that sigma square. So what is it?
1.5 into 5 sigma square.
Yes?
Yes, sir.
This is the, not just the covariance of this thing, but the variance of xt actually is 1.25 sigma square. Yeah, and this is when S equals T, R S T becomes this. Let's try when S equals T,
Plus variable.
let's say minus 1.
Minus 1.
Yeah, what does that mean? That means that S minus T equals
0. 1. Sorry. 1.
is it 1 or so?
T minus S equals
T minus S equals
Equal to
1. Yeah, so the difference is 1. For convenience, I will just from here on write it like this. S minus T equals 1 in this case.
Yes.
Yeah, and the other case to have this would be S equals T plus 1. Now try those.
Yes.
Try any of them. Yeah, so what do you get now? What happens to the first term?
0.
0. All of a sudden now things are changed. What happens to the second term in this case?
Variance of
minus 1.
So T minus 1, T minus 1.
0.5 variance of
Yeah.
variance आ जाएगा हमारे पास
Right?
sigma square.
Okay. What about this one?
variance of
Same आ जाएगा सर 0.5 sigma square. No.
Yes, sir. S minus 1.
S minus 1 है ना.
Yeah, S is T minus
Zero
1.
हो
Put
जाएगा
T
सर.
minus 1 here. It's T minus 2.
0
ये भी 0 हो जाएगा. What about this guy?
0.5 S T.
Also
ये भी
0.
सर 0 हो जाएगा.
Also 0, right? Or not?
0 हो जाएगा.
हो जाएगा या नहीं?
सर
So this should be 0.5.
sigma square.
Basically only this term is left.
सर 0.5 या 0.25.
नहीं वो it appears only once here.
Yes.
Okay, so tell that. Okay, what about S equal T plus 1? Now
First one
this
is-
term will play the role of this term,
Yes.
right? बाकी सब 0 हो जाएंगे. So it will again be 0.5 sigma square. Now try S equals T plus 2 for example, just to see. What do you get? Clearly this should be 0. clearly this should be 0.
Yes, sir.
Yes or no? Agreed?
Yes, sir.
Clearly this should be 0.
Yes, sir.
Clearly this should be 0. And clearly it should be same for any t plus 3, 4, 5. So now we are ready to write the covariance function of this R in a general form. We say RST equals 1.25 sigma square when S minus T was 0. It was 0.5 sigma square when S minus T was 1, right? And 0 otherwise, right? So meaning S minus T absolute is greater than 1. Yeah. So that means this guy really doesn't depend on the S and T. It only depends on the difference, which you already saw when you told me that x11 and x12, the adjacent ones, will have a covariance, but if you go to the next ones, they won't. And now we found that any adjacent ones have the same covariance. So we can rewrite this as now saying R tau equals 1.25 sigma square for tau equals 0. It's 0.5 sigma square for tau equals 1 and it is 0 otherwise.
The difference of 2 times is also a time. So why it is not dependent on a time? We are saying it is dependent on the time difference. ये हमारे पास S पर या Y पर आपने कहा कि नहीं डिपेंड कर रहा, हालांकि ये दोनों पर डिपेंड हो रहा है.
नहीं कर रहा. देखिए, it would depend on S and T only if the knowing S and T matters. Do you need to know S and T to solve this thing? Let's say I tell you that, I don't tell you S and T, I tell you that S minus T is 5. Can you answer this question? What is the covariance? You will go here.
Yes.
I tell you S minus T is 1. You come here. Did I get S minus T by 11 minus 10? Did I get it by 100 minus 99? I didn't tell you. Actual time was never mentioned. ये डेटा आपने आज सुबह इकट्ठा किया था, ये शाम को. Yeah, it didn't matter. As long as I'm talking about, okay, when you collected this data, in that data, any two adjacent ones are correlated by this much, any two further ones are not correlated. Yeah. So it may look, that's why we normally get rid of S and T completely and we just put a tau here to remove the confusion also. But again, as you see here, the actual value of S and T did not matter. Yeah. So x11 and x12 have the same covariance as x100 and x101. Yeah. What does that mean? Remember जो मैंने example when I started with stationarity, I said two of you go to collect this process. One of you collects here, the other one collects here. Yeah. And would they come up with the same first and second order statistics for Whiteson stationarity? So if it is actually Whiteson stationary, both of you will come with this formula, right? दोनों का result एक ही आएगा. You will come up with the same covariance function. You will say, yeah, any two adjacent points have a covariance this much. Anything further, 0. You will come up with same RST. He will come up with same RST. Yeah. So it won't matter that this was actually x11 and this was x12, and for your case it was x100 and x101. Right? So so what did we conclude, by the way? What are the lessons learned here? Firstly, moving average processes are
Whiteson stationary.
one thing. Yeah. Second, anything else we learned? They have a vanishing covariance function. Yes, so moving average processes, their covariance function disappears as you go farther away. So in fact, this was a first order moving average process. There are processes there whose covariance is vanish after 5 points. Okay, so you could define a moving average process as ut plus 0.5 ut minus 1 plus some other weighting ut minus 2 plus, so you could have 5 of them, and if you repeat this thing it will turn out to be Whiteson stationary, and its covariance function will have value up to s minus t equals 5, and then it will become 0. Yeah, so this is what we call a vanishing covariance. So now if I tell you that this guy is a moving average process of order 1, you already know that this is Whiteson stationary, and you know that any two, I am drawing continuous, but you can have it whatever you like. So I'll have to check, but I think there is no need to assume that this has to be discrete in time. Okay, because you could have a continuous set here. Okay, t could be from the real numbers. Okay,
But if it is, then it is very hard to tell from the very next number if t is different.
yeah,
So you tackle this.
yeah. So I think you will need to limit it somehow. We can. I will check. Okay, to see. But let's see. In this case, you have. If you have this is xt and this is xt plus 1, then these two have some correlation, whereas if you have to go to the next one xt plus 2, this will have no correlation with the original. Yeah, okay, so let us see. How much time do we have? So we can see one more and then we close it for today. If I plot the covariance of this MA1 process with tau here, then at 0 it was 1.25 sigma square, right? At tau equals 1 and minus 1, it was what? 0.5 sigma square, right here, yeah? And then at any higher taus, it became 0. So if you just try to draw it like that, or even if you don't, you can see this is what's happening. The covariance is vanishing. Now for a fifth order, what will happen? The covariance will keep going down but continue till the 5 and minus 5. After that, it will become 0. Okay.
If we increase very much large, then it will become a Gaussian sample.
You could have something like that, yes. If you increase very much, it will still be asymptotically decaying. Gaussian doesn't really imply what is here in the covariance, right? It has no link here in this scheme, yeah, because we are drawing not the density function. This is वो जो आप लिंक कर रहे हैं उससे वो तो that is PDF on the x-axis ना. This is not PDF on the x. This is covariance function, yeah. Right. So a Gaussian process can have different kinds of covariance functions. So that is a different domain के the PDF is Gaussian. वो एक और कहानी है. Right. So let's see if we can cover this next one. So we have done what? Firstly,
Sinusoidal.
is sinusoid with random amplitude. Yeah. Then we did moving average. The first one was not Whiteson stationary. The second was Whiteson stationary and had a vanishing covariance. Yeah. Then we go to a random harmonic oscillation. okay, which is the generalization of the first case. And this is what's going to happen now. We have a random process xt coming from, again, some sinusoid 2 pi with a frequency, let's say fixed frequency f naught t, nothing random yet. Okay, now the random things will come. It has a random amplitude and it has a random phase. This is the new thing. We already did this part, right? But now these two are random variables. Firstly, we're going to assume that they are independent of each other. Who? A and phi are independent of each other. Right. Further, we are going to assume these two things to make this, keep this applicable or interesting. First assumption we are going to make is that the phase, which is a random variable, is uniformly distributed in 0 to 2 pi. So the phase takes values in 0 to 2 pi and they are equally likely. Yeah? Okay. For the other random variable a, the only assumption we want to make is a is greater than 0. No other assumption we need. And together they are independent. Okay, they are independent of each other. Sometimes orthogonal we try to write or summarize it like this. Yeah. So, but this is the starting point. Now, what do you think? Is this, firstly, what does this process really look like? What do its realizations look like?
Sinusoid.
Each realization is a sinusoid. That's clear. Yeah. So, but how many? So again, I would say this is a continuous random variable. Okay. So a greater or equal to 0, but a can take values in real number as long as it, so it's positive real numbers. Yeah. Okay. So then, how many realizations does it have? Too many. Infinite.
Infinite 0.
But yes, minus 1 or 1 can be.
-1 and 1
Oh,
can,
it's amplitude has a.
yeah. So then we have no put no other assumption on it. Yeah.
I was just considering
Yeah.
the range of force.
Yeah. So then, how many realizations? Infinite. Yeah. How do the realizations vary? How are they different? Can I draw one realization here? Let's draw one.
Yes, sir. Start from.
So let's say there is one realization like this that has some amplitude, let's say 1. What is the phase?
Phase
0 to 2 pi.
Now, which in this realization, what have I drawn? Phase is?
0 to pi.
So cosine is 0 at cosine this phase is pi by 2, I think I have
Pi by 2,
drawn.
yes, sir,
Yeah,
0.
because cosine has to start here. Yeah.
Yes,
So it could be like this. Yes. What else? What other realization could it have? So now I have drawn this realization is a is 1 and phi is pi by 2. Because cosine, na? So pi by 2 makes it a sine. So I've drawn a sine basically. Yeah. What else? No.
Oh,
It
we
could
can
be
keep on
1.5,
and-
but the same phase.
Yes.
Yeah.
Yes, sir.
That's another realization. What else?
Now we
It
can-
could be 1
and 0.
but 0 phase. Yes. बनता जाएगा ये तो खिचड़ी पक जाएगी यार. What is happening? You have control over two things. Shift it like this randomly. Yeah. Each time, each realization may pick one of these values, and you can magnify it or attenuate it. Yeah, like that. So you have control over the amplitude, which is random now, and the phase. So you can imagine what it looks like. It's not that nice one that we drawn before, where this was only allowed to have two values, Now its randomness is showing in amplitude and in the phase. So, and the phase doesn't have to be 0 and pi, it can be anything between them also. Yeah. So it could even, let's say, be starting like already started here, so coming down, and so there's so much going on. Yeah. All of these are the realizations of this random process. Now the question, is it White-Sands station? What's your guess? Remember पहला वाला नहीं निकला था. Yes? So what's your guess by the way?
If that was a special case, that was not a Variance station, so obviously that will not be a Variance station.
Right. Special case, it wasn't really a special case in the sense that it didn't have another random variable, right? Okay, so firstly I'll give you the answer, then we will derive that. This process is White-Sands station. It will pass both our tests. Okay. So let's see. And the answer is, remember the previous one, there were only two realizations and the mean was changing. Now imagine this thing. The amplitudes everywhere, the phases everywhere. Already you can see at any given point everything happens. So the mean should, all the means will become 0 actually, or whatever, one value. Yeah, because of this shifting. Okay, and we will see because also allowing more of these, but not just that, the covariance will also turn out to be independent of the actual points. Okay, so it will depend only on the difference. So let's see, start with the mean. Can you find the mean of xt here? कैसे करेंगे find? आंसर तो मैंने दे दिया कि कोई कांस्टेंट आना चाहिए, राइट? व्हाट
एक्सपेंड कर लेंगे कॉस को,
करें जरा एक्सपेंड. Firstly, what will you write? So you know what you have to find. Yeah, you have to apply the expectation operator to this guy. So that is E A cos 2 pi f naught t plus phi. Yeah. Up. What's your first step?
कोसाइन को सर हम लीनियरिटी प्रॉपर्टी लगा रहे हैं या कोसाइन को एक्सपेंड कर लें सर.
Should that be a first step or something before that? How many random variables here?
2
A and phi. Right? Are they independent?
Yes.
They are. So you could first use this information to separate. Right? आसान हो जाएगा ना? Now you are dealing with one random variable at a time. ये बड़ा important information होती है ये independence की. Yeah. So expected value of A, whatever it is this negative or positive value?
Positive.
Because A was always positive. So we don't go into what value. Let's call it mu A if we want. So it has some mu A is a random variable, so nothing changing with time, just mu A. Yeah. What about this? Yeah, now this is interesting. What do you think is the expected value of this thing? Now we have taken away the random amplitude thing. Yes. Now if you imagine what does this random process look like in different realization, it has a fixed, if you just look at this thing, it has a fixed amplitude 1. Yes. So ये जो ऊपर नीचे ये खत्म हो गया. All is left is, all of them have amplitude 1, except now that they are sometimes starting here, sometimes like the phase is different. Yeah, phase is changing. So yeah, all of those Desarevo, you make all of those. Now what's your guess? Just by looking at these things,
The cos phi expectations are
even
going to be
you know,
zero.
even some phase will sometimes come here. Yeah, because we are allowing all phases. So imagine थोड़ा मुश्किल होता है draw करना bias in your book also. So it has all these. What can you look at if you देखें इसको अगर वैसे guess करें? What should be the mean value at any given point?
0.
Zero से निकलती है ना? Just intuitively imagine it. You actually will find it mathematically that this term, this factor is 0. Then I want you to imagine it also.
Yes.
Yeah, same amplitude, but because of the so much variation in the phase, it sometimes is here, sometimes here, sometimes here, sometimes here. Almost all is possible. Yeah.
Yes.
So actually this is 0. You can show it mathematically. कैसे करेंगे इसको सिंप्लीफाई करने का कोई इतना तरीका हमारे पास है नहीं है. We'll have to go back to the definition of expectation. Not much we can do here. Okay. I think you said expand into like cos alpha plus
Yes,
beta like that.
Cos alpha plus beta, then sir, इसके ऊपर apply कर देंगे expectation cos phi के ऊपर.
Yeah, you could try that, but I have it here like this, so try it. Well, let's see what you get. But for me, this one, I will do it like minus infinity to infinity cosine 2 pi f naught t plus phi times, what's the definition of the expectation? The random variable times probability. Yes.
Uniform distribution.
This we know is, what is it?
Uniform 1 over 2 pi.
1 over 2 pi, right?
Yes, sir.
Because it's continuous, it goes from 0 to 2 pi. We know that this area has to be 1, so the only way it will be 1 is if this is 1 by 2 pi. Yeah, so we know f phi is 1 over 2 pi. So then we put that here. 1 over 2 pi will just be coming out of there, right? And then you will have let's see, so I have replaced this with a y so that we have a index here, and then we have cosine 2 pi f naught t plus y, 1 over 2 pi goes there, dy. What next? So the area under this thing, yeah, the y takes what range of values?
0 to 2 pi.
0 to pi. So the integral can be simplified to, remember, this is the range of the random variable.
Yes, sir.
What is this? Anybody can tell? Yes, the area under a cosine over one whole period is always 0.
Zero, yes.
Negative or positive cancel out हो जाते हैं ना.
Yes.
Phase doesn't matter now. We're talking about one whole period. Wherever you start, complete the period. So all the positive parts will cancel the negative parts. So without solving this integral, आप solve कर सकते हैं, not a
Yes,
problem.
sir.
But even without solving it, you can argue. We know it is going to be
Zero.
0. So then this whole thing became 0. So that's the first thing you have shown now, that the mean is, yeah, mean is well, constant. We were interested in showing is it time dependent or not, right? It turned out to be 0, which means it is constant in this case. What about the covariance? How can you find that? So you will start with EXSXT. Yeah. So if you start with that, you will have a cosine 2 pi f naught s plus phi, and with a cos 2 pi f naught t plus phi. Yeah. And there you will have to you will get a square, and then because they are independent, you will separate them. Finally, there are several steps in there. Okay, it's in your book, Lindgren. Just go through that. I will skip the steps. And mathematical juggling है like this one, but bit more complicated. Okay, you will be dealing with not one but two. So होता है ना product का cos, and you are able to वो करना है. So yeah, I don't want to go into that, right? But you get the idea. Eventually, it will come out to be the expected value of xs xt will turn out to be half EA square cosine 2 pi f naught okay. Notice I did not write the covariance of xs xt. In this case they are the same. Why?
Variance of
xs xt is the same as expected of xs xt. वैसे generally तो ये true नहीं होता ना. There is another term here. More terms here. So because the x is zero mean, now we can drop that part. Yeah, that's what happens. So whenever a process is zero mean, the covariance can be simply reduced to expectation of the product. Okay, when the process is zero mean. If it's not, then it doesn't hold in general. Yeah. So but since I know it's zero mean, so I not know, we actually proved it already. So then I am able to write it like this. What did we get finally? So this was RST, right? But notice in solving this we concluded that S and T don't matter. Yes? Notice as you will the covariance has to be symmetric also. Is this function symmetric also? Yes, cosine is a symmetric function. याद है?
Yes.
Minus की value, so it actually not, it doesn't, if it is 1 or minus 1 or 10 or minus 10, this cosine है ना?
Yes, sir.
So ये अगर यहाँ sin आ रहा होता ना तो it would fail the test of a covariance function. कोई गलती होगी आपसे, or it's not Whitesands stationary. Yeah, but here it is Whitesands stationary. And what did we find the R to be? So we found that R tau. Now we can replace here. Yes, S minus T with tau. So it was E A square cosine 2 pi f naught tau.
Yes.
Yeah, I took this step only after proving that this is Whitesands. You can never go here without first proving that this is Whitesands stationary. Once you have proved, that includes the proof that it depends only on S minus 2 absolute, then you can replace S minus T by tau. So now this process, which is, its name is a random harmonic. Okay, random harmonic. Actually later we will look at sum of random harmonics, which will lead to something very critical, power spectral density. We will come to that towards maybe 7th, 8th module of the course. But here it is just one random harmonic. Later we will make it a summation. Yeah. So, but notice here something interesting to notice here. What is that? This will come in handy later. You know Fourier transform, right? Let's say this was not random and this was not random. Then you're dealing with a deterministic process, right? कोई fixed value है, variable है लेकिन random नहीं है, yeah? So what would the Fourier transform of this try to give you? It will try to find this frequency content, right? Summary karo mein. There is some argument, we will come to that. But you know, the Fourier transform of a random process does not exist. Okay, because the Fourier transform क्या करता है? Integrate करता है, yeah? Yes. But in a random process, these have so many different values that the total energy is infinite, so you cannot actually integrate. Okay, so what we do a trick. We will come to that later. ये मैं detail में आऊँगा वापस. But for now, what I want you to see is something very curious and interesting here. Notice that this random process did have a frequency in it, yeah, which was f naught. Notice the frequency of the covariance function. The covariance function is also a sinusoid, and its frequency is same.
Yes.
Yeah. In fact, if we had a sum of random harmonics, so let's write this one quickly and then we close it. So now we are going to the next level. We say that we have a sum of random harmonics, which is a k cosine 2 pi f k t plus phi k. Okay, k is 1 to n. A naught, a k. See, all of these a's are random variables with what was the requirement? They were greater than they had positive values, right? So these are random variables and these are random variables. They are all independent of each other. So even a naught is independent of a1, a naught is independent of phi1. All of them are independent of each other. This random process is a sum of k plus 1 sinusoids. This is a sinusoid with zero frequency.
Yes.
Right? Cosine 0.
Random sinusoid.
Yeah. Yeah. So a sum of sinusoids with random phase and amplitudes. Right? So that's one thing. But with that, we also assume that all phi k's are uniformly distributed in 0 to 2 pi, just like before. Yeah, and they have finite variances, the EAs, all that. So with that, I'll skip the details. But you know, this will also turn out to be a wide sense stationary process if you prove all the steps. And its covariance function, any guess from there what the covariance function will be? Let's say the E a k squares have variance sigma k square, yeah, like that. So this will be sigma naught square plus summation, or I could still write a, but anyway, sigma k square by 2 cosine 2 pi f k t. Okay, so the covariance function of a sum of random harmonics is also a sum of harmonics which are not random. Why aren't they random now? ये तो fix है ना this.
Yes, sir.
Yeah. So, but the interesting thing, whatever frequencies these guys had, this guy had. So when we come to the Fourier transform of random processes, we will find out that this cannot be directly Fourier transformed because of mathematical issues. What we can do is use a proxy. For wide sense stationary processes, the proxy is the covariance function, because the covariance function has the same frequencies, okay, with the amplitudes replaced by the variance. Yeah, so it's like replacing something by its moment. बहुत सारे values and you replace them by the variance and average mean. Yeah, so but this is a whole topic. We will come to that maybe after 2 more modules when we go to power spectral density. Okay, and that will be a direct extension of Fourier transform to random case. What you have learned so far in transform techniques, most likely all of that you learned was for deterministic processes. Okay, but for random processes we have to extend it to a different through a different approach to get here. But here I just want you to see, look how beautiful it is. If xt is a sum of random sinusoids with these conditions, of course, that have frequencies f0, f1, f2, then their covariance function will also be a sum of sinusoids, not random, and the same frequencies. So if you take the Fourier of this guy, you can still see the frequency content that was supposed to be there in the original random process. That's a very powerful thing in studying random processes in the frequency domain.
We will use a conventional Fourier transform to this covariance.
Yeah.
Because it's a deterministic model.
Yeah, exactly. यही तो हुआ ना. We took away the whole issue. Yeah. But now this is just like whatever any transform you have learned, just apply it here. Yeah. Okay. So that's just a trailer for what will come maybe after some lectures. Next lecture, Markov chains and renewal processes, which will be our, this was third example.
Yes, sir.
And if we count this, we will not count it as fourth, but this is a third one. Then there is fourth, there is Markov chains, then there is fifth is random walk, and we will keep going like that. Okay, so let's see, next time we'll try to cover maybe 2-3 of them. Okay, so and stop this.